Yeah. Hi, everyone. Thank you for coming for this gRPC Open Telemetry talk. I'm Purnesh Dixit. I work at Google in the gRPC team, and I'm the maintainer in gRPC Go.
Hi everyone, I'm Saurabh. I also work at Google in the gRPC team.
Yeah, so today we are going to walk through the gRPC's Open Telemetry plugin that we have recently created and how to achieve distributed tracing with it. So why do we want observability? Well, so assume you got some services deployed in a distributed system, and these services talk to each other on various user actions or just to achieve some task. So there are often certain questions we end up asking ourselves when we are debugging a service. Uh, is the overall system behaving as expected? Is there something wrong going on? If there is something wrong, where do I look at to figure out what is wrong going on? Another common scenario is to debug the overall system performance and figure out where the bottlenecks are. So why is something going slow or whatever? Okay, great. So let's say we have set up the metrics and we have gotten a dashboard for ourselves to look at. But we cannot expect a human to continuously be looking at these dashboards, right? So if something goes wrong, we want to be notified. And so we set up the alerts as well. This is a brief intro on, or a very brief intro on the gRPC observability. Like if you're a gRPC, if you have gRPC application, this is something uh, you will get out of the out of the box from the gRPC libraries. Uh, so let's say you have an app developer, the character at the left in green, maybe it's Saurabh, and he's building a gRPC application using the latest gRPC artifact supporting observability. The running apps are provided with appropriate observability configuration by the developer. Uh, the gRPC interceptors, so interceptors basically sits right next to your application code, and all the RPCs going in and out kind of goes through them. Uh, so they they intercept those RPCs, pump the relevant raw data like logs, metrics, and trace information, and through various exporters, they will be put into the respective backends. So here you see a logging backend, a metrics backend, and a traces backend. Uh, the backends basically produce the required dashboards which are used by the consumer. In this case, the DevOps engineer to get visibility into the internal state of application, uh, focusing on gRPC traffic. Now, I'll invite Saurabh to talk a little bit about OpenTelemetry.
Thanks, Punesh. So, at a very basic, OpenTelemetry is an open source CNCF incubated observability framework which lets you create and manage your telemetry data. So, it allows you to do metrics, tracing, logging, and this is one of the sample of practices from one of the service. So OpenTelemetry solves a very key problem in tracing, which is vendor lock-in. So irrespective of whether you want to export your matrices from Google or AWS or Datadog, or you have your own custom solution, you can do that using OpenTelemetry. So how does OpenTelemetry solve this problem of vendor lock-in? So basically, they provide standard set of APK, SDKs, APIs, and data formats for collecting and exporting your telemetry data. And once you have the standard format, then you can change your configuration just to match which backend you want to export the data to. So imagine you are using a proprietary monitoring tool. If you decide to switch to a different vendor, then you will have to basically switch to that vendor's APK, that vendor's agent, and you will have to make a lot of changes to your code. But if you're using OpenTelemetry, then you don't need to make any changes to your application code. What you can do is you can directly just change the configuration for where your data, telemetry data needs to go. So just the configuration for backend needs to be changed, and then you're good to go. Yeah, so OpenTelemetry is an industry standard, basically supports all popular solutions are supporting OpenTelemetry, and this is the direction in which things are moving. So Jaeger is there, like Grafana, everyone is there. So all major languages are also supported. Yeah, you'll see your favorite language there. So we have created a few code labs for like having some quick practical experience. So highly recommend to go ahead and follow these code labs. Yeah, I'll wait. Yeah, okay. Yeah, okay. So understanding the life cycle of a request. So trace is what helps us to understand the life cycle of a request within your application. So we have tracing, which gives us a lot of information. What happened when your request went through your application, which was like basically a lot of microservices, and what happened to that request. That is, all that information is within a trace. So that's the first part of tracing. Then obviously, when you are when you are in dev environment or staging environment, you can basically trace all your requests. But as you will move to the production environment, you don't want to trace all your requests because tracing can be expensive. You basically, if you trace every single request, it will be expensive on on your CPU as well as the data you will collect. So what you do is you sample requests, 1 in 1,000 or 1 in 10,000 requests you sample, and then just trace those. And that also will give you the same amount of information to debug your service or see what is happening in your service with a lot less kind of expense, like spending less on the resources. Okay, so let's dive into exactly how the tracing part works. So at the heart of trace is basically a single request going through the application. Its journey is tracked by a trace, and then trace is further divided into smaller spans, and each span is like a small distinct unit of work. It could be a database query, it could be a API request, or it could be some other CPU intensive application you're doing. And each of these spans can be individually tracked, and then you can figure out exactly what is going wrong or where you have a performance bottleneck. So by piecing together all these spans, we have a comprehensive understanding of what exactly happened in the complete life cycle of the request. Yeah. So distributed tracing also provides a very strong visualization for each of the requests. So you see like the timeline for the request and it going through multiple microservices within your distributed system. It looks like something like this in your timeline. I'll go. Yeah, it looks like this. So here you will observe that it's a dummy hipster shop ecosystem service which we created, and you can notice that a single request flow goes through multiple services like currency converter service, product catalog service, get card service, and yeah, how they are dependent on each other. And if we go, like, if we drill deep into this timeline, we will see that the get card service is the one which is taking the most amount of time. And So now we can focus on this, and maybe working on this will improve the performance of our overall service the most. Yeah. So now I'd like to invite back Purnesh for.
Thank you, Saurabh. Uh, so we'll dig a little bit deep into what the gRPC OpenTelemetry plugin provides you if you are using that to instrument your gRPC applications. So first we'll talk about the client. So when you instrument your gRPC client with OpenTelemetry tracing, you get deep visibility into your service communication because you are talking to multiple services. So that's where the gRPC kind of comes in. And it automatically generates two types of spans for you. Maybe people who are already using OpenTelemetry would know about these spans. So there is one is like call span that represent the overall gRPC call end to end, and there are attempt spans which detail individual retry attempts in case you have intermittent failures and the gRPC is retrying to connect for you. And these spans kind of capture rich information about the gRPC interaction, including timing, status, and metadata. Crucially, key context like trace ID, as Saurabh showed, the trace ID, which was the global key for all the communication that has happened in the service lifecycle, request lifecycle, is what gets propagated throughout wherever till where the request is going throughout the RPC lifecycle. And there are span IDs as well, which are basically from one service to its next caller, where you propagate the span ID of that particular span that made the call. And that kind of enable you to trace requests end to end and understand the complete flow within your distributed application. And that's how you see that hierarchical tree kind of structure that Saurabh just showed you. Now, first we have is call span. That represents, as I said, the overall gRPC call, regardless of the retries. And it contains high-level information from call start to call end. For example, if there was a resolution, if there was a delay in name resolution, then what was the RPC status, whether it failed or it succeeded. And this is, as I said, this part gets propagated to the next service. And this is crucial for distributed tracing because that is how you connect the dots from one service to another. So suppose you see a delayed name resolution complete event. When you have instrumented your gRPC application, you see that event kind of coming in your logs. And let's say it took like 5 seconds to resolve the target host. What would you do? So your first thought would be like, okay, there is a delay and that could be caused by some network issue, or there are some DNS problems, or maybe the service discovery. If I'm using a service discovery, it might be just overloaded or something. So you would look for like potential solutions, including maybe optimizing your DNS lookups or using a more efficient service discovery mechanism, or maybe implementing a caching. Having this information kind of make you focus on where the bottleneck lies in. Then there is something called attempt span, which I previously mentioned, that contains some more detailed information about what happened in that particular service as part of the gRPC service communication. So this represents a single attempt that was required to make the call. And if there are retries, you will see multiple spans emitted. And these will be nested within the call span. So each attempt span will be the child of the call span. And if there are more retries, then you will have multiple spans which are children of the call span. And these attempt events in gRPC kind of help users to pinpoint the root cause of failed calls. So you saw there is a failed call, but you want to know like what exactly failed or what exactly made it slow. So providing this information about retry attempt, it could be like load balancing delays, message sizes, compression. So this allow you to target optimization and troubleshooting of your gRPC applications. And this information, the attempt span doesn't get propagated to the next service because attempt spans are internal to that particular client which is making the call and don't directly relate to the server side processing. So let's say you saw something called delayed LB pick complete. So if you are using gRPC, this is a very common event that happens in gRPC service communication. And then you will see how these span traces is helpful because it is explicitly showing you if your load balancer decisions are slow. And that is what causing your gRPC application to have high latency. Or it could be that the load balancer itself has some performance issues which are not under your control. So maybe load balancer is overloaded, or there are network issues, or maybe load balancer is just misconfigured. So if you're seeing this event, that's where you have to look in. Similarly, like you have previous RPC attempts. So as I was saying, if there are retries, you want to see how many retries happened. So anytime number of retries happens, this will be captured in this field and you will see it. And these can help you identify the flakiness, intermittent failures, and examining the sequence of messages that are sent and received across multiple attempts. And that kind of reveals the patterns in how the application and its dependencies are handling the errors. Okay, now if we move to the server view of the gRPC OpenTelemetry plugin. So the key point here is there are no attempt span for server because the server doesn't deal with retry. So it only has a single server span per gRPC call because it is just accepting the call. And the context propagation here is just one way as well. So server receives the tracing context from the client, but doesn't need to send it back. It will just send the response back that, okay, I got the message, but it doesn't have to again send the tracing context back to the client. So this here we basically show a server span captured by OpenTelemetry during a gRPC call. So as you can see, OpenTelemetry automatically instrument gRPC, and you can see the message flow and the timing based on these events. So the outbound message sent, for example, marks when the server sent a message to the client, which is to respond, okay, I got the request. And OpenTelemetry captures useful attributes here, like basically the plugin, that sequence number, message size, and whether it was compressed. Similarly, the inbound message received event indicates when the server received a message from the client with key attributes like size and compression. So these granular level of details helps us understand message exchange patterns and identify potential bottlenecks related to message size or compression, and pinpoint any errors that occurred during the communication. Finally, the stream closed event with its status and description tells us how the gRPC call concluded, whether it was successful or encountered an error. And then if there was an error, you go back to the previous spans, like outbound message sent or inbound message received, to identify the pattern. Okay, so this slide is basically talk a little bit about how the OpenTelemetry plugin in gRPC is implemented. So as you can see, the primary piece of information from the gRPC service point of view is the span context, and it is the OpenTelemetry span context. So just going back where Saurabh was mentioning that why gRPC, why OpenTelemetry is the service standard, and this is where the standardization happened. This OpenTelemetry span context is a constant 29 bytes header, which has a standard key called trace parent, and that key all the vendors understand, all the exporters understand, and all the exporters know how to differ this span context 29 bytes, and where are the trace ID, span ID, and how to connect them. So that is how it achieves portability. So basically, trace ID is just a unique identifier that you saw that link all the related spans across services. Then span ID is the ID of the current span. This allows the next service to create a new span that correctly parented to the incoming call span. Then there are some flags, which are some key value pairs that can carry some additional context that maybe you want as an application user to provide. So basically, when from the user's point of view, what you all the only thing you have to do is when you create the gRPC client, you provide the text map propagator, which is basically an OpenTelemetry object that allow you to inject the span context and extract the span context. And you do it at the time of creating the client. So you cannot do it at the runtime. And once you do that, your gRPC application is instrumented completely. So that's the only thing you provide. Now, this is something which is the implementation details of OpenTelemetry plugin. So you can see like the text map propagators, once you have instrumented your code and your RPC is running, the OpenTelemetry plugin code kind of executes at the interceptor level. So from the client's perspective, when your application logic has finished and your RPC is just about to go, this plugin will intercept that, and it injects the OpenTelemetry span context into the header, which is basically the metadata header. And there are two types of keys gRPC deals with. One is a gRPC trace bin key. Maybe people who are using OpenSenses might know about this, because this key basically is like a binary header that captures the information in actual bytes. So this OpenTelemetry plugin that we have designed handles both gRPC trace bin binary header as well as trace parent, that is W3C context header, which is standardized by the OpenTelemetry. So this text map propagator once injects the header in the gRPC context, and it uses a carrier object, which we will see later in this presentation, that how it gets used. And this carrier is doing nothing but putting the data directly into the gRPC metadata. And it can be either a string object based on what type of header it is. If it's a text header, it will just directly put it at the string. If it is, and there are some language specific implementation difference. So if, for example, in Java and Go, we basically base 64 encode and base 64 decode the binary headers. But in C++, we just directly store the bytes. And then once all this text map propagator and the carrier work finishes, this data is just put it into the wire as one of the header in the gRPC metadata. Then at the server side also, at the start, when you are creating your server object, you configure your server. So basically, you will just provide a server option with the text map propagator, and then your gRPC server is instrumented. And this at the server side, like in the client side, we saw there was something called inject. In the server side, we have something called extract because we are extracting the span context that is coming from the previous service. So again, the gRPC OpenTelemetry module will have this carrier, which will. So now you can just mirror the previous image where there was gRPC trace pin, there was gRPC propagator and carrier. Now the carrier will come before and it will uh, extract the header, which is basically coming from the wire, whether it's string or bytes, and it will handle both format, and then it will give it to the text map propagator, and then text map propagator will make sense of it and create a open telemetry span context out of it, which will be again those 29 bytes object, and it will be readable. It will be provided to you as an object, and then you can create the parent-child relationship through that. The key thing here is that why the text map propagator is a different object. I'm sure many of you have that question, like why can't you just have get and set inside that, right? So the reason is that it allows you to bring your own propagator as well, because eventually we want to make it more pluggable. So the job of the carrier is just to read the metadata and put the read the metadata header and put the metadata header. What you want to do with that header can be different based on what are your application requirements. So you can either use the text map propagator that gRPC provides, which will just read it and put it into the gRPC context. But you can also bring your own propagator and do some more transformation using that. So that makes it more pluggable. This is a simple API, as you can see. There are just two options that you provide. And both of these options are provided at the time of creating the client or the server. So if it's a client, then you will provide it as a dial option. And if it is a server, you will provide it as a server option. So tracer provider is something which OpenTelemetry SDK gives you. And it allows you to like specify how much you want to trace, like the sampling logic, what type of global key you want to use for the exporter, to and how you want to configure your exporter, whether you want to use a console exporter or you have some endpoint where you want to send all your traces. All these things kind of gets configured in tracer provider. And then text map propagator is something which gRPC gives you out of the box. You can either use that or bring your own propagator. Then the OpenTelemetry plugin code is very simple as well. You can see that it takes the context and carrier, and then it will set the header and the span context in a binary format when it is the client, because a binary format or the string format, so that it can be put into the header. And at the extract function is for the server. It basically decode the bytes that has come in. So it reads the header, it decodes the byte and gives you the OpenTelemetry context header, OpenTelemetry context object. You can see the carrier. So this gRPC trace bin propagator is designed to handle both binary header and the text header that is trace parent. But you can bring your own propagator as well. The carrier is very simple. It just has get and set. This is something internal to gRPC. So whatever propagator you are bringing in will be using this carrier, and it will only have string headers. So that's where it will only have string values, string key value pair. So if it is a binary header, we will convert it into a base 64 format and then put it into the gRPC metadata. If it is a string header, like which is a W3C context header, then we'll just directly put it in the string. But OpenTelemetry has enforced to deal only with text headers. As of now, there is no communication or whether there will be binary header support. Okay, so that's kind of the current status of OpenTelemetry tracing. We have the design complete, and Java already has an experimental API in 1.68 version. And C++, Go, and Python are in active development. So yeah, that was a whirlwind tour of gRPC OpenTelemetry. We hope you like to dig some more into this. And in 2025, we'll be holding a gRPC conf in India for the first time, likely in Bangalore. And details on that will be announced soon. We hope you will be able to attend and gain an even deeper appreciation for gRPC or OpenTelemetry, whatever your interest is. Beyond that, there are various ways that you can connect with the gRPC project. And yeah, we look forward to see all of you in gRPC Conf.